Hey y'all, it's Mr. Johnson. I've owed y'all this video forever, so here it is. This is the finding key functions, key parts of functions assignment. Many of you have already turned this in. Good on you. If not, here's some help. All right, let's use our knowledge of first and second derivatives to find all the key points of a graph, right? We've got a function. Let's graph our function. If we do it pretty sloppily, it looks something like this. If we do it not sloppily at all, it looks exactly like this, right? So actually, let's make it go under, whatever. We just plugged that into Desmos and it worked. Great. New color. Use the power rule to find the derivative. This is when we take the exponent, multiply it by the coefficient, and knock the exponent down by 1. So this one would be 2 times 2 is 4, and then 2 minus 1 is 1, chilling at 4x. Linear terms that only have an x get taken to just their coefficient. We'll graph this in a different color, say blue, right? And we'll do this here kind of not sloppily, but, not caring if we're super accurate. Third thing, we use the power rule again. This is, again, we say the coefficient times the exponent is 6, and we knock this down by 1 to get 1. And when it's x to the power of 1, we just kind of say it's x. And then linear terms go to their coefficients. Constant terms go to 0. And then we graph it either on Desmos, it's going to be a straight line, and it's going to be right here. Or we graph it on our piece of paper, and we just kind of guesstimate a little bit. Great. And again, you can take your graph here, screenshot that, bada bing, bada boom. You're good. And now we've got to ask ourselves, let's bring this down so we actually know what we're talking about. So I just have all this information all there so we can see what we're doing. Where are the local maxima on the original graph? The original graph is the purple one. We're looking for the local maximum right here. We can do a bunch of fancy algebra, or we can go on Desmos, click this button, and see that it's negative 1.9. That's kind of what I'm looking for here. You might notice that the negative 1.9 stacks up directly with this derivative's 0, right? The maximum of the original function is the 0 of the derivative. And this should come as no surprise to you because it kind of matches up with this. We already know. For the local minima, just do the same thing. Click on the red function, find its minimum, write it out. I'll let you down by yourself. Is there an absolute maximum on this original function? Let's take off the derivatives just so we can focus on this. Local minimum and local maximum are when you're bigger than or smaller than everything around you. Absolute minimums and absolute maximums, or global mins and global maxes, are when you're bigger than everything. And there's not really going to be anything on this function that's bigger than everything because it goes off to infinity. So here we'll say no absolute maxes. I'll let you figure out if there's any absolute mins. Where are all the points of inflection on the original graph? I actually need to add a few lines here. Points of inflection on the original graph are maxes and mins on the derivative, which means it's where the second derivative is equal to 0. So asking where are the points of inflection, we could rewrite this question to say, where is our second derivative equal to 0? And this is just like an algebra question that you solve for x. 8 through 12 are all going to turn into these algebra questions. We can rewrite number 9 as over which intervals is the slope of your function increasing. So we look at slope, we look to where it says increasing. And that means we can either change this question to where is f concave up, which to be honest is still a hard question, or we can change this question to where is, again, increasing, where is f double prime positive? Which means where is 6x plus 4 bigger than 0? And this is now something we can solve and write in interval form. I think you can do this one. Because it's kind of the same as number 9. What's really almost the same as number 9 is number 11. Because when we change the question, original graph, concave up, we're also highlighting this same row. We're basically asking the exact same question as number 9, which means we'll get the exact same answer. Pretty good, right? Whereas f concave up is the question we could have asked right here. We could have said, where is f prime increasing, which literally was the question for number 9. And then we could also say, where is f double prime bigger than 0, which is what we ended up answering. In a similar vein, number 10 and number 12 are the exact same question, and thus we'll have the exact same answer. Hopefully that clears things up. If you need more help, please message me on Teams or come to office hours. Bye, y'all.